Here we see the formal method of integration by substitution. We just remember that the relationship between the thing we're integrating and the answer is that the answer, when we take the answer, we can differentiate it to get the integrand. So here our integrand is the f prime x, which is x squared. We differentiate 1/3 x cubed plus c to get x squared. Written as an integral, we have the integral of x squared dx is 1/3 x cubed plus c. We differentiate the answer to get the integrand. Another way to write that is with the notation dy by dx. dy by dx is of course another way to say f prime x, and then we can call our answer y as a function of x, or we can just say y. We just change the notation and we've said the same thing again. We do that to show what it would look like if I had written it in terms of u instead of x. If I have a derivative expressed with the function as a function of u, then I can anti-differentiate with respect to u. So we'll do the exact same relationship. If dy by du is u squared, then y will be 1/3 u cubed plus c. All we've done is change the letter. We haven't changed the mathematics. So written in terms of u to the power of 2 du is 1/3 u cubed plus c. Let's return to this problem we looked at in the last video, where we have a composed function. When we differentiate it, we end up with a product, and with the product we have here, we see du by dx is 2x minus 4 and dy by du is cos of that. So suppose that we're trying to anti-differentiate a derivative, and the integrand is expressed as a product. Well, we know that the chain rule is also expressed as a product, so let's suppose then that the derivative is actually the product which is created by the chain rule. We'll find out if it works or not partway through, if on a certain step we end up with a function of u, or a mixed up function of u and x, in which case our idea fails. So suppose we have du by dx, which is a product. What if we divide that product by, divide it by du by dx? All we're left with is dy by du. So if we can simplify our integrand to just the function of y with respect to u, we can anti-differentiate and find y. So let's lock this in place before I edit it. Okay, so here we're going to say that the function u is x squared minus 4x plus 5, the inside part of the composed function. So the derivative of that is 2x minus 4. Now suppose the integrand is found by the chain rule, then the integrand is x squared minus 4x plus 5 multiplied by 2x minus 4. Divide all of that by du by dx, and we find out nicely it cancels, and all we're left with is a function of u, cosine of u. And so we anti-differentiate with respect to u, sine u plus c, sine x squared minus 4x plus 5 is what we said was u, which is what we said earlier. Okay, so let's formalize that into 8 steps. Okay, first we're going to identify a composed function. Here we have cos of x squared minus 4x plus 5, and we'll identify the inside part of that is x squared minus 4x plus 5. We call that inside part u and differentiate it. We'll state the integrand as a product dy by du times du by dx. Divide everything by du by dx. See if we are left with a function of u, or if we get a mixed up function, in which case our method fails. Then anti-differentiate with respect to u. So here we're going to work 6 examples, the same examples as last time, but this time using the method. So first we have to identify the inside part of the composed function and call that u, and calculate du by dx. Now we'll state that the whole integrand is a product dy by du times du by dx. And now we'll divide the whole integrand by what we've calculated to be du by dx. So we're left with a function of u. That's nice. We can anti-differentiate our function of u with respect to u, and replace the u with the function of x, and our job is done. If we want, we can check that by differentiating. Okay, our second example, we clearly see we have a product of two functions of x, so perhaps one of them could be described as du by dx and the other dy by du. Let's find out if we could. So we spot the composed function. I've rewritten it so that it's easier to see the first step and the second step. So let u be sine x, then the derivative of that is cos x, the whole integrand as the product. And now let's divide all that by du by dx. And again we see the top and bottom of the common factor, and we're left with just a function of y, which is the derivative dy by du. So anti-differentiate that with respect to u, and replace the u with the function of x, in this case is sine x. And then we can check that out, differentiate that to see if we are left with the integrand that we started with. So our composed function here is something to the power of 4, and the inside part is circled in red. So we'll call that part u, and differentiate that. And so let's say the whole integrand is a product dy by du times du by dx. Let's suppose if that's correct, then when we divide by du by dx, we'll be left with just something about u. If we're not correct, we'll have a mixture of variables, and either we'll have to be creative or try a different technique. So here we're just left with u to the power of 4, anti-differentiate u to the power of 4, and now finally replace the u with the function of x. And if we want, differentiate our result to see if we're right. Okay, again, it's not so obvious in the integrand where the product is, so I've written it as a product of 1 over x multiplied by ln squared. So we identify the inside part of the composed function and call that u, and differentiate that. The whole integrand, suppose that's the product, dy by du times d by dx. We'll find out if that's a fair thing to say when we try to divide it by du by dx. And yep, again we're left with just the function u squared. Anti-differentiate that, and replace u with the function of x. And check that by differentiating. Here we have the derivative of tan x, the antiderivative of tan x. We'll start by writing it as a product, and the composed function is actually 1 over cos x, the first step being take cosine, the second step saying 1 divide. So let u be the first step, cos x. Differentiate that, we get negative sine x. So let's write the whole integrand as the product dy by du times d by dx in this way. And now let's write the whole thing again and divide it by du by dx. And we see we have a common factor of sine x. Let's not drop the negative. And we end up with negative 1 over u. We anti-differentiate that to ln absolute value plus c. Replace the u. And then we can try and differentiate that to make sure that we're correct. So we have a new result that tan x is equal to negative ln absolute value cos x plus c. That's interesting. Okay, so finally, number 6, writing it again as a product. It's not obvious where the composed function is here. So we write that to the power of 1. So we notice that 1 over x is the derivative of ln x. And writing the whole integrand now divided by d by dx cancels out nicely. We're left with just a function of u, just u in fact. So we're anti-differentiating u squared divided by 2. Let's replace u with ln x. And you can again differentiate that. In fact, the last two examples can be generalized into the form that we have a derivative divided by f of x dx. We let u equal f of x, then du by dx is f prime of x. And then when we take our integrand and divide it by du by dx, we find that we cancel top and bottom, and the bottom is just a function of u, and that's what we're left with in general. And so we can say absolute value f of x plus c. It just generalizes the process of example 5 for tan x. So here's an example. Let's go x squared minus 4, and the top, say 2x, which is a derivative of the denominator, and according to our rule, the antiderivative will be ln x squared minus 4x.